Hey dudes, welcome back to my channel, Salamat 2020. Before we proceed to our presentations, please don't forget to subscribe and hit the notification bell just to inform and notify you kung meron tayong mga new uploaded math tutorial videos. For today's presentations on PreCalculus about writing and evaluating sums in Sigma notations. In this lesson, we will see the power of these notations in computing sums of numbers as well as the algebraic expressions. We will also answer the questions here. How do we write and expand sums in Sigma notations, and what is Sigma notation used for? Okay, we have the given series here, 1 plus and 1 half plus 1 over 3 and so on. Then up to 1 over 100 can be expressed as the compact form, that is Sigma notations. So the Sigma notations is a simple form of shorthand using to give the concise expressions in writing sums of the values of a variable. And we have also the summations, or the Sigma notation can also be evaluated or can also be expanded into expressions, and we may even simplify it if possible. So let's expand the more concept of summations in our next slide. Okay, alamin muna natin yung konsepto ng ating writing and evaluating sums in Sigma notations. By the way, Sigma notation was invented or introduced by Swiss mathematicians and physicists Leonhard Euler. Mathematicians use the Sigma notations, denoted as the uppercase Greek letter, that is a symbol sigma, is used to indicate the sum. The notation consists of several components or parts. This is also called the summation notations. So, given the expressions f of m plus f of m plus 1 plus f of m plus 2 up to f of n can be compressed or written in Sigma notation. Okay, that is these notations. Given this notation as summation notation f of y. Okay, how do we read this symbol? The summations of f of I from I is equal to m to n. Here, m and n are integers. Ibig sabihin, a number or numerical value where m is less than or equal to n. The value of m mas mababa kaysa value ng n. And the f of I is a term, or what we call this, a summand of the summations. And we have also the variable I is the index of summations. And each value starts at m. Okay, dito yung magsimula ang value ng ating variable I, which is also known as the lower bound, increases by n and ends at n. That is what we call the upper bound. Okay, for example, okay, how do we read this given examples? This is the summations of 2 raised to k from k is equal to 0 to 5. The 2k is the term of summand, the formula for the terms, and 0 is the first value of k, that is lower bound, and upper bound is 5. The last value of k. Okay, so let's do our first example. So example number 1 is expand each summation and simplify if possible. So number 1, the summations of a quantity 2i plus 3 from I is equal to 2 to 4. So the formula of the term is 2i plus 3, and 2 is the lower bound and the upper bound is 4. Then copy the formula, that is 2i plus 3, and it will start with our lower bound, that is 2. Then just continue, copy the term of the formula 2i plus 3 up to the upper bound, that is 4. Then substitute the value of I. The first term is 2, then for the second term is 3, and the last term of the upper bound, the value of I is 4. Then get the product. 2 times 2 is 4, plus 3 is 7. Then 2 times 3 is 6, plus 3 is 9. Then 2 times 4 is 8, plus 3 is 11. Then get the sum of all the terms. 7 plus 9 plus 11 is equal to 27. Okay, for number 2, so the summations of the square root of n over n plus 1. So we're using the variable n here from n is equal to 1 to 6. So the term or the formula for the terms is square root of n over n plus 1. The lower bound is 1 and the upper bound is 6. In first terms, copy the formula square root of n plus 1, and it will start the lower bound, that is 1. Just continue, copy the term of formula up to the upper bound, that is 6. Then keep substituting different values of our index. So we have the value of n is 1. Then a second term, the value of n is 2. Then the value of the third term is 3. Then the value of n, that is 4 terms, 4 up to the value of n is 6, which is our upper bound. Okay, the last value of n. Let's simplify each term. The first term is 1/2. Then second term is square root of 2 over 3. Then third term is square root of 3 over 4. Then square root of 4, that is 2 over 5. Then plus square root of 5 over 6. Then last term is square root of 6 over 7. With this result, so we can describe sums of the multiple terms using sigma symbol or operator. So these are our terms given the summations. For number 3, so we're using here the variable j, the summations of a quantity j squared minus j from j is equal to 3 to 6. The term of formula is our first term, j squared minus j, and it will start with our lower bound, that is 3, then keep on writing up to the term of formula. The value is 6, which is upper bound. Then keep on substituting the different values of our index from 3 to 6, which is our upper bound. Then simplify all the exponential form here. So 3 squared is 9 minus 3 is 6. Then 4 squared is 16 minus 4, that is 12. Then 5 squared is 25 minus 5, that is 20. 6 squared is 36 minus 6 is 30. So get the sum of all the terms. 6 plus 12 plus 20 plus 30, that is 68. This time we have the writing sums in sigma notation. So how do you write an expression in sigma notation? So given a series here, x plus x squared plus x cubed plus x raised to 4 plus x raised to 5. So we know the exponent of our first term is 1, equivalently to x. And this series can be represented as compact form as sigma notation. So how do we write this series in compact form? So check each term. So each term has the variable x, so that could be our formula of the term. Then we can use the I as the index of summations, and our lower bound start with 1, since our first term is 1 up to 5. Then we can use the exponent of the formula of the term is I, that is represent our terms. So let us check. If I is 1, so that is x. If I is 2, x squared. If I is 3, x cubed. Then I is 4, x 4, and I is 5, x raised to 5. Okay, so that is the result from series to summation. We have another series for number 2, positive 1, negative 2, positive 3, negative 4, positive 5, negative 6, up to negative 10. So we can express this in a compact form. That is sigma notations. We can use here k as the index of summations, and it will start with our lower bound, that is 1, up to 10, which is our upper bound. And since we have here the alternating sign, that is positive and negative, so let us find the role for a sequence of this symbol, positive and negative. So the alternating signs of the sequence, the term of such series, usually have a factor of negative 1 raised to k plus 1. So let us check. If k is equal to 1, that is 1 plus 1, that's 2. The negative 1 times negative 1, that's positive. So positive. If k is 2, negative 1 raised to k plus 1, then 2 plus 1 is negative 1 raised to 3. This is equivalent to negative. So that is our second term. That is the role for a sequence of alternating signs, positive and negative. So we can use the term formula, that's negative 1 raised to k plus 1 multiplied by k, which is our integers. Start with our lower bound from 1 to 10. Okay, so let us check if this compact form is satisfied with our series. So if k is equal to 1, then we are using the formula of the terms negative 1 raised to k plus 1 times k. So substitute the value of k, that is 1 plus 1 multiplied by 1, that's negative 1 squared times 1. So since negative 1 squared is negative 1 times negative 1, that is positive. Then write positive 1 multiplied by 1 is equal to 1. That is positive 1, which is our first term. Then for second term, if k is equal to 2, we are using the formula negative 1 k plus 1 k. Then substituting the value of k, that is negative 1 cube multiplied by 2. So negative 1 cube, that is negative 1 times negative 1 times negative 1, that is negative 1 multiplied by 2, that is negative 2. So that is our second term, negative 2. So it is satisfied the compact form in our given series. For number 3, so we have a series here and expressed in the compact form or the sigma notation. So our first term is a sub 4, second term is sub 8, third term is sub 12, then fourth term is sub 16. Then factor the numbers, 4 times 1, 8 is 4 times 2, 12 is 4 times 3, and 16 is 4 times 4. So we have the k here is a lower bound up to the upper bound, that is 4. Since we have the same numbers, we can write as a sub 4 as our formula of the terms of the summations, a sub 4. Then we have the index, the upper bound, lower bound up to upper bound, that is k. So the summations is a sub 4k. So let us check. Then if k is 1, that is 4 times 1 is 4. That would be our first term. If k is 2, then 4 times 2 is a sub 8. That would be our second term. So it's satisfied as a given series to sigma notations. For number 4, so this could be the example of arithmetic sequence. So 1 plus 4 plus 7 plus 10 plus 13 plus 16 right into sigma notations. So our first term is 1. So we can write as the index of summation is equal to 1 up to the upper bound, which is 6. Then we can use the formula for the arithmetic sequence. A sub n is equal to a sub 1 plus the quantity of n minus 1. So our a sub 1, the first term is 1. The common difference, that is d, between the consecutive terms, the 4 minus 1 is 3. Then 7 minus 4 is 3. 10 minus 7 is 3. So that is the common difference. That is 3. Then simplify for the formula of the terms. So 1 plus 3 times n is 3n. Then 3 times negative 1, that is negative 3. Then copy 3n, then 1 minus 3 is negative 2. So the formula of the term is 3n minus 2. Then the summations is 3n minus 2. So let us check if n is 1. So 3n minus 2 as our formula, then n is 1. 3 times 1 is 3 minus 2 is 1. So that would be our first term. If n is equal to 2, 3n minus 2, then substitute the value of n. 3 times 2 is 6, minus 2 is 4. That is our second term. So you may continue for the n values. Okay, dudes, we have here a prepared activity for you to practice what have you learned from our Sigma notations. Make this channel as your home of learning. Thanks for watching and God bless us all.